This program is brought to you by Stanford University.
Thank you, and thank you for the nice introduction. And actually, it's a great pleasure to be here, especially the nice weather. I think it's snowstorm back in the East Coast. So the title of the talk today is on renewable ocean energy conversion systems, and particularly about how we can advance the state of the art. Actually, the reason why I picked this picture on the title slide is because you can see that the ocean actually covers more than 70% of the Earth's surface. So it's an enormous renewable energy potential source, and is one that we haven't fully explored yet. I mean, especially compared to wind and solar. So so that's why the title of the talk today is on different types of ocean energy technologies. The focus will be on moving water resources. So in particular, I'll briefly introduce you to different types of energy conversion systems for ocean wave, tides, ocean and river currents. There are also other resources that can be categorized under ocean energy conversion systems, and they include like offshore wind, offshore solar, thermal, geothermal, salinity gradients, and marine biomass, but I will not talk about those in today's seminar. Okay? So if you look at what kind of initiative we have in the US in ocean energy technology, the Department of Energy just directed to establish a program on marine and hydrokinetic technology program. So they target, this is under the Energy Independence and Security Act of 2007, and this targets specially for marine and hydrokinetic energy. And under this act, in September 18 of 2008, they have just announced an award up to $7.3 million for research and development of clean energy technology for water power projects, including some on energy development, market acceleration, and 2 new marine energy centers. Actually, I work with colleagues at University of Hawaii as well as at Oregon State University. So what do they mean by marine and hydrokinetic renewable energy? So specifically, that includes wave, tides, currents in oceans and estuaries and tidal areas, free-flowing water in rivers, lakes, and streams, and man-made channels, and also ocean thermal energy. Specifically, though, they exclude the energy from any source that uses a dam or a diversionary structure or some kind of impounding structure for power electrics. So I will not be talking about dams today. So just sort of an overview of this presentation. First, I will talk about different renewable ocean energy conversion systems for waves. They generally can be categorized into like terminators, attenuators, and point absorbers. And then I'll cover the other type of where you take advantage of kinetic energy for ocean currents, river currents, et cetera, and tides, and specifically about tidal turbines. Okay, and then I would like to focus on horizontal axis turbine in particular, and I'll explain. So what are the difference between a wind and a marine turbine, and why you can't just put a wind turbine in water and hope that it works, and how do we design them, and then what are some design challenges that we are facing today for these structures. So the first part is I just want to briefly introduce you to the different type of technology. So the first one I want to cover is ocean wave energy. So the force the wave reverses every 4 to 20 seconds, depending on where you are in the world, and it's driven primarily by wind. So it can be predicted up to days ahead, and so it's a variable source, and there's a diverse range of different types of energy conversion devices. I'll show you a few, and the global electricity potential estimated by IEA OES is about somewhere between 8 to 80,000 terawatt hour per year. So here are two that you can see. The one on the left is called a Sea Dragon. This is what we call terminator. So basically, the device is aligned in a direction that's perpendicular to the direction of wave propagation. So it traps the water. And in particular for this device, if you see the graph on the lower left-hand corner, the overtop wave, it fills the basin, and then the water, it gets collected, and the gravity, it releases it down, and it drives a hydro turbine underneath, okay? And another type of device is called attenuators, and they're aligned along the direction of wave propagation. And if you look at the picture on the right over there, you see that basically the wave height is different along the segments, for example, from the crest and the trough of the attenuator. And the differential motion basically causes flexing of the joints. And by flexing of the joints, it powers actuator units, such as some of these actuators. And then that's how you can convert it into power. So it can take advantage of heave motion as well as yaw motion moving like this. And another type is called point absorbers. Basically, they are floating structures, and they take advantage of relative motions. So you have, for example, another cylinder tube in there. It can, for example, have compressed air, and the wave motion causes it to heave up and down. And you can drive it, you can convert it using electromechanical, or it can use to drive some kind of turbine. It depends on how do you design such systems. So two examples are the power buoy or the aqua buoy type of converters. And you can get a sense of the size of that one on the left. You see all the people standing there. So besides wave energy, you also have what we so-call the ocean current energy system. So you can see the drawing of the current driving around the world. And these are relatively steady, and it's unidirectional Gulf Stream with a high velocity core. And this is driven by wind and solar heating near the equator, and the deeper currents by salinity and density gradient. So the typical energy conversion device for this is actually underwater turbine. So since I would like to focus on turbines, I just want to show you the various applications that it can be applied to. And here is the artist's drawing of some of these turbines. This is an open turbine, sort of like, almost like a parachute, but you cut it open. So, if you talk about ocean current energy, the global electricity potential is about 50 terawatt hour per year. So besides that, you can also take advantage of river current energy. So this is governed by rain, right? Depending on how much rain, and it flows down the river. So it's very stochastic in nature. So some cons about it is you have very large sediment loads. You can, if you go out in the river, you can see that. And you may also run into debris or ice impact. Now, and it's also difficult to schedule maintenance because you don't have scheduled slack, okay, compared to tides. But the beauty about it is unidirectional flow. So your device doesn't have to adjust in pitch and directions. And the typical energy conversion device is such as this, is again a turbine, basically a submerged turbine. This one is actually applied for the Roosevelt Island Tidal Energy Project by Verdant Power. So the US electricity potential for this is approximately 110 terawatt hour per year, according to Miller. So in addition to ocean current, river current, you can also take advantage of tidal energy. And so the tidal energy is basically produced by the centrifugal force caused by the Earth's rotation and the gravitational attraction of the moon primarily. And, but tides are bidirectional. You have flood tide and you have ebb tide, right? It retreats. So your device gotta be able to take advantage of the flow going in both directions. So it's a little bit more challenging. But the advantage to that is that it can be reliably predicted. We have been predicting tides since for over 1,000 years, right? There are typically, we all know tidal barrages that can be applied for these type to extract the energy from the flow. But I'm not going to be talking about barrages today. Instead, I'm going to be talking about tidal turbines. Here is a graphical drawing of this. And so the tidal global electricity potential for tides there's varying estimates, is approximately 1,800 terawatt hour per year. So you can look at one of these, if you go to the internet, you can pull many of these nice pictures, and you can see that there are many places around the world, including the US, where you have really good tidal potential, where the velocity is greater than, where the tidal range is greater than 2 meters, for example. And the velocity can be greater than 2 meters per second. So here is specifically for US, you can look at different sites. And since we're in California, you can look at the Golden Gate Bridge site in San Francisco. And over there, the source potential is 2.1 terawatt hour per year. So since you see from all of these that turbines, we rely on turbines for many of these energy as an energy conversion device for different types of currents. Okay, so what are the different types of turbines then? You have horizontal axis turbine, and you have vertical axis turbine, and what we so-called alternative device. So a horizontal axis turbine is, these are some examples. You can have one with a straw on it, different kind of mooring. The advantage of that, of horizontal axis turbine, is that we can borrow from very advanced technology from the wind energy industry. Okay, and the nice thing is about it is generally self-starting, so you don't need something else to power, so it's really clean, right? And it can be supported from the top or from the bottom. For example, it can be inclined, supported by a floating structure, or you can moor at the base. The disadvantage about this is that if you're talking about for ties, because you have the bidirectional flow, the flow goes in both ways, it needs some kind of yawing device so that basically it needs to be able to rotate in direction to account for the change in direction of the flow. So vertical axis turbines, there are two general categories. One is the lift. It looks like 8-beater. So these basically, it works with the same principle as a turbine. Basically, flow goes to the cross hydrofoil section, and then it generates lift perpendicular to the flow, and that turns the device. But preferably, the angle of attack need to change as it rotates. If not, you need to, it needs some kind of power to start it. So, and the drag type device, the water pushes it and then it turns. So they tend to be less efficient, much less efficient. So the advantage of these is that it's omnidirectional. So that you can see that the flow can come from any direction. So you don't need any kind of yawing mechanism. And it can be mounted at the base or the top. So if you talk about for ocean applications, if you mount it at the top with a floating structure, the advantage to that is that you don't need a support tower, and you can also put the generator on the top, so you don't need underwater cables, okay? And so it's easier to install, easier to maintain, and so you may have reduced overall cost. But there's also, there's always a yin and yang side of it, right? So the disadvantage is that is poor, usually it requires some kind of power to start, and it tends to be less efficient than horizontal axis turbine for the same area. And based on the experience from the wind energy industry, they have not been shown to be commercially successful. And there are some reasons. I mean, you don't, if you drive out in California, go to a Mojave Desert, for example, you see wind turbines, you don't see 8-beaters, right? So you don't see this kind of stuff either. Well, there are some reasons to it. One is actually very simple, because usually for wind, you're mounted at the base. So at the base, the velocity is 0 right at the ground, right? So you don't have very large flow velocity to begin with. So that's part of the reason, but it's also not very efficient. So that's why you don't see many of them. So besides horizontal axis turbine and vertical axis turbine, you also have a whole range of alternative design. Every day you will have somebody come up tell you they have a great new idea. So, but not many of them actually make it to the grid or make it to the commercial stage or even just to like a full-scale project. So on the left side, you see one is so-called the lifting or flutter vanes. So basically when the flow goes to, it generates lift. This is a hydrofoil, similar to an airfoil but in water, and it creates lift and it just moves up and down, okay? And you can use that to convert to energy via different kind of actuators or electromechanical device. And you also have another one. This one was developed actually at Michigan, University of Michigan. I visited over there. It's actually pretty cool. they test it in a wave tank when the flow goes through. When the flow passes to a cylinder, it actually oscillates. And this is actually due to vortex-induced vibration. And this is the reason why, if you don't want this to occur, if you see tension link platforms, they have little scags over here to break the von Karman vortex. But this device was purposely designed to take advantage of the vortex-induced vibration, and so it really moved up and down really fast. It has been tested in the laboratory, but it still needs to be validated for full scale, and how do you support it is another question. So these are some, I'll show you some current turbines in a little bit, but just some note about the industry learning curve, okay? So it takes generally about 5 to 10 years to turn any kind of conceptual device into a commercial application. So 2 decades ago, the wind energy costs, depending on which estimate, this is from IPRI, they say 20 years ago it was 20 cents per kilowatt hour. Department of Energy, they say 20 years ago it was 80 cents per kilowatt hour. But anyway, that's 20 years ago. Today it's about 4 cents per kilowatt hour. So you can see that there has been significant improvement, and this is due to research and development. Okay. And so marine or ocean energy or tidal energy is actually entering the market at a cheaper cost of energy. And this is largely due to we can borrow a lot of the advanced technology from the wind and also from the propeller side. So just to show you how wind energy has developed over the years, this is a graph, and this was produced by a report called 20% Energy by 2030. That's one of the goals of Department of Energy. You can see just in terms of the design from 1980s, 50 kilowatt, all the way to the design that we have now is 2.5 megawatt. You can see that it has changed significantly, but the turbine size has grown tremendously. So it from around 20 meters in diameter all the way to around 100 meters in diameter. So if you go offshore, it's like 140 meters in diameter. So actually, the reason why I'm showing you this is because in the design that these large wind turbines got to consider is very similar to, they run into the same problem for turbines in water, because it has to take a tremendous amount of load, and then you have to worry about them moving in the air, okay, the structural aspect. And the flow is actually greatly varying. So if you look at Department of Energy, they have this report. They want to significantly grow the wind energy potential. We're in 2008 right now. This is what they project to be needed in order to meet the 20% energy need via wind energy. So, and they have also talked about putting in waters. There are also existing commercial plants right now. So this is just a picture, and you can see that in order to put wind turbines in water, you have similar issues as putting in water turbines. How do you support it? So they're dealing with a lot of these similar issues. So the advantage is that we can take advantage a lot of the research and development that will be put into this area, and that has already put into this area, into the design for ocean energy conversion system. There's a lot of overlap. Okay. So since I talk about the similarities, now what are the differences? What is the difference between a wind and a water turbine? So on the left is a wind turbine. On the right is a marine current turbine. You see that they look very similar. They exactly like what you say, a beef up version in the water. And why do you need to beef it up? The reason is because the density of water is 840 times denser than air. So now if you talk about a device with the same efficiency, power efficiency, the power density, basically the power per area for the sweep area that it takes, it's like about 4 times greater. So this is the one for wind, this is the one for air. Or it's about 3 to 4 times higher. So you don't actually, if you want the same power rating, let's say you want a 1.4 megawatt design, you don't need such a large turbine. For wind, if in order to achieve 1.4, maybe you need something around 50 meter in diameter. For water, all you need is 25 meter in diameter, so much smaller. But notice that even though the capacity, the power capacity is about the same for these two designs. Notice the drag force, the force that is transferred, the thrust, transferred to the structure is much higher. Compared to 253 kilonewton, now I have to take 1.5 meganewton. So much higher load on the structure. So you really have to think carefully when you design the supporting structure. So what are some different pros and cons when you compare a marine or a tidal turbine with a wind turbine? Tidal turbine in particular, the nice thing is tidal energy is highly predictable, like I say, but some of the cons about it is very technically challenging. You have to design the blades, the controllers, the gearbox, all of these stuff, and the support structure, right? And, but wind turbine, the large scale, you also have to worry about the support structure for offshore. So there are some uncertainties for tidal turbines. Yeah, resource, it depends on the resource. You need undersea cables, grid networks, and stability. And so on the other hand, you also have the advantage that you have a much higher power density because of the higher density of water. But you have to worry about how do you select the site and how do you design the turbine. And you also need to test it in the field and how do you deploy it. There's more cost to that and operational maintenance, okay? Another advantage is that it's lower visual impact. It doesn't obtrude your, it's not like on land and you see it right in front of your house. It's beneath the ocean and you don't see it. So, but now you're operating in harsh sea environment. You can have marine grill. You can have, for example, you have to worry about corrosion, et cetera. And you also have to worry about slow permitting process and a high initial cost. Put anything in water to drill and to put is much more expensive. And so there are uncertainties about market acceptance and the impact on the environment and marine life. However, there are also another advantage is that you have tremendous crossover potential from wind turbine, but the design of tidal turbine is more challenging. You have higher loads. For tides, you have bidirectional flow. You have the harsh sea environment, and you have to worry about cavitation. I'll explain what is that. And then there are also uncertainties about potential vessel impact if you have a ship hitting it, or interaction with surface wave, the bathymetry, et cetera. So here are some examples of some some current or marine or tidal or river turbines that have already made it to the grid. So there are different designs. For example, Landstrom, you can see these are all horizontal axis turbines. So it's different types of design. So there's two that I want to focus on particular. One is the CGen project. This is what they claim to be the first commercial scale tidal turbine. You can get a sense of the size. These are people over here, and these are the blades, okay? So you can get a sense of the tremendous size of these. About 15 to 20 meter in diameter. They rotate about 10 to 15 RPM. Their initial cost for the Strangford project was about 16.8 cents per kilowatt hour. They project when it's fully developed, it will be about 5.2 cents per kilowatt hour. So it's really becoming comparable to wind. And this is a project in US. This was actually, that's the Roosevelt Island project that I told you about earlier. These are, the pilot project was 5-meter diameter rotors, and they put out 6 of these, okay, in the river. What happened is they put out 6, they lock in a number of hours, but when they put it in there, actually, you see that it broke. So they fell due to structural issue. This is what I mean. You cannot just put a turbine in a wind turbine, just put them in water and hope that it works, okay? So they realized that they really have to worry about the strength issue and the tremendous load they gotta take, right? So they redesigned it, and now the new blades are made with solid aluminum magnesium, and they're getting permits for installing more turbines. So what are some challenges with the design? So you have much higher loads, like I say, because of the higher density. So you have to worry about strength, you have to worry about fatigue, you have to worry about vibration, and then you have to worry about stability issues, right? And for tides, it's also more difficult because you have bidirectional flow. And you have the tidal boundary layer effect and then interaction with surface wave, bathymetry, et cetera. So you have like a flow constantly changing. It can change in directions and it varies with depth. So you need some kind of active and passive control. You have a harsh sea environment. You have corrosion. You have to worry about barnacle, sea growth. You have to worry about sediments, debris, and then you have to worry about potential vessel and ice impact. Another thing that's unique about putting in water is you have to worry about cavitation. Cavitation is intermittent, and then it can cause damage to both sides of the blade surface. It can significantly decrease the performance, which I'll show you in a bit, lead to erosion, noise, and vibration. So what is cavitation? It's similar to boiling. Everybody knows boiling. You increase the temperature to 100 degrees Celsius, and then you get bubble formation, you get boil. Cavitation, on the other hand, basically you achieve it by reducing the pressure. Okay, and so when you reduce the pressure, when it reaches the saturated liquid vapor pressure, it forms a bubble. The formation is okay, but when it collapses, it actually forms a microjet that treads to the bubble, and that jet, the velocity of that jet can be up to 1,000 meters per second. Now, this is actually used for example, like lithotripsy to break up kidney stones. You can use it to break up brain tumors. You can also use it to cut things in water. But there's now, if you put it on a blade, in the marine propeller side, we have to worry about it because it can really damage your blades. This is an example. It can cause severe erosion. It also causes a lot of noise. You probably don't want that. So here's an example of a tidal turbine that was tested in a cavitation tunnel, and then you can actually see the cavitation right at the tip over there. Okay. So how do we analyze and design these then? So there are different methods. Traditionally, you have basic momentum theory. Basically, we know that the turbine extracts energy from the flow. You assume it as an infinite disk. And then so the streamline has to expand. And then from there, you can calculate what is the change in pressure. So the classic theory is by beds. If you use this, you can estimate what is the optimal power. For example, we know that the optimal power is 59.3% of the limit because the velocity reduces because the streamline expands, but it will not reduce to zero, okay? So, but the problem is you cannot design what is the optimal geometry of the blade from there. So there's what we so-called blade element momentum theory. So basically you use a momentum theory, very simple analysis, to calculate the axial and circumferential velocities. And then you look up a table. So you can pull out a table and you see what is the lift and drag coefficient of different blade sections. And then you integrate it to get the thrust and the power. However, that cannot account for 3D effects. You have what we so-called vortex methods. Basically, they represented either with a line, the blade with a line, so they don't account for the chord, what we so-called lifting line, or lifting surface method, where they only model the mean camber of the blade. And so it can account for three-dimensional effects, but it's not good at the leading edge. And the leading edge is very important because that's where cavities will form. And traditionally, this has not been a problem for wind turbines, so they didn't have to worry about it. And wind turbines have geometry that tend to be very slender and beam-like, rectangular, so they don't need to worry about three-dimensional effect either. But for marine propellers, we have to worry about that. So in terms of that, the technology development is more advanced in the marine propeller side, and also because the Navy has much more money to do this kind of research. So a more advanced method than that is panel method, or what we call boundary element method. So we actually panel the blade. You can see that instead of the mean camber surface, we actually panel the surface of the blade. So we really account for the actual geometry, okay? And so we can capture the details at the leading edge and the tip more accurately. And that's the one that I will focus on because it's very fast. Now, if you really want very advanced technique, you can use CFD methods. So you can use RAND solver, and Navier-Stokes solver, all these fancy ones. This is the example. I have this project with, this is another project of mine funded by the Navy with University of Minnesota. So you can see if you were to do this, much more expensive. Just look at the grid around the blade. It's amazing. Just to do one of these calculations, it can take weeks to months. So you don't want that in the design stage. That's way too much, okay? So instead of worrying about I think a panel method is sufficient in the design stage, but that only computes the fluid load. Now, how about the structure? I told you before that it can break. So you can see that if you have very high loads, it can lead to like the strength failure, fatigue. You can have excessive deformations. It can also snap. This is a wind turbine, and this is a marine current turbine that has snapped. So you have to worry about the forces acting on them. So I think it's more important to do the analysis so that you design for both the hydrodynamics and the structural dynamics. And so what I'll show you in a bit is a boundary element method and finite element method for those. I'm not going to go into the detail about it, but basically, it's a very fast method. I can basically do a computation like in about somewhere between even a fully coupled like 5 minutes, so it's really fast. So you have the flow coming in. The idea is that we use a potential-based method. So basically that assumes the flow to be irrotational, but when it's rotating is, how do you account for the rotation effect is by using an effective weight, which is basically the inflow without the propeller plus the vertical interaction with the propeller. And so basically you solve it, you have conservation of mass and conservation of momentum. And this is this example of this is a boundary layer flow. For example, the velocity decreases with depth. Here's your hub, here's your blades, and this is the weight surface, for example. And we change it so that we only need to change it to a boundary value problem instead of solving for the volume. So you end up solving for the integral equation. Now, how do we mathematically, just some very simple basics. You have to make sure that you have the no penetration boundary condition so the flow doesn't penetrate the blade. And you also apply that condition to find the thickness of the cavity if you have a cavity here. And the pressure of the cavity must equal to the saturated vapor pressure. We also have to make sure that the flow velocity is finite at the trailing edge. And we have to find where the cavity detaches and where the cavity reattaches, because the cavity grows and collapses, okay? So there are some details about that, and that's where in the wind industries, in the wind turbine side, they don't have to deal with that. You don't have cavitation in air. So in water, we have to deal with that, and we're used to doing that. So there are some details about how to find the proper length of the cavity and the proper detachment point. And instead of explaining the details, I just want to show you why is it important to do that. Now, this would be, for example, this is the pressure on the suction side, and on the pressure side, the pressure coefficient on the hydrofoil surface. So now if you don't account for cavitation, you get this kind of pressure. And the lift, the lift and drag depends on the area within that's cross overlap area between these two curves. You can see that if you actually consider cavitation, you will have a very different lift and drag between the two. So that's why it's so important to be able to properly predict it, in addition to all the other damage that cavitation can cause. So to validate the method, I have compared with like experimental measurement. This is for a marine current turbine that was tested inside a cavitation tunnel. You can see the tunnel here. We also do this for propellers. You can see the blade. And you can change the hub to the blades at different angles, pitch angles. And so this is some comparisons with experimental data. Experimental data is these. This is the power coefficient for two different hub angles, and then the numerical prediction is the one in the field symbol. So you can see that it compares very well, the field symbols and open for both the power coefficient as well as the thrust coefficient with experiment. So I know the method works. And the nice thing is, most of them, if you look at search to literature, the methods, they don't consider cavitation. So the nice thing about this method is that you can actually predict the cavitation. For example, this, I'm just plotting as lines over here. You can see this is where the cavity is forming, and it looks very similar to what was observed in the experiment. And if you don't account for this, you get this kind of pressure distribution. Just looking at the color, you can see that they're very different, okay? So what happened when you have cavity form? You have the cavitation form. Now if you calculate the resulting thrust and the power, you have this red symbol instead of this blue. You can see there's a decrease in power and then decrease in thrust. So, okay, so that's the reason why you need to be able to predict cavity properly so that you can avoid it. You want to do a design that you avoid cavitation so you don't have this decrease in performance, you don't have noise and vibration and erosion associated with it. So all these is for hydrodynamics. Now, how do you deal with the structures? I have came up with a way to how to do the couple fluid structure interaction couple simulation by basically decomposing the motion, the velocity due to rigid blade motion and then due to elastic blade motion, and then do the same thing for the pressure. And if you integrate that, you end up with this equation where, for those of you who are familiar, you can get an added mass matrix with structural mass, hydrodynamic damping with structural damping, and this is acceleration velocity, and then you have stiffness and displacement, and you can solve for this equation to get the structural stresses and displacements as well as eigenfrequencies, for example, and you can deal with composite structures, okay? So if I use this and I go back to the same turbine, I analyze it, what I realize is initially I try to design it using nickel aluminum bronze, which is a very common material used for marine propeller. And what I realize is you got 1.2 meters of deflection. That's not good, okay? So if you actually do a 20-meter diameter, it's actually pretty big. So the load is very high. If I actually find that I need a minimum of a very high strength, and it needs to be corrosion resistant. You can't just think about any kind of metal. So I decided to use the iron, chromium, nickel, copper alloy, which is a high strength corrosion resistant alloy. This Young's modulus is 196.5 gigapascal. And if you do this, then you see that the maximum stress that you get is 411 megapascal compared to yield strength 1.17. So it's okay. So it's safe, but you still have very large deformation, about 70 centimeters. So it's about 7% of the radius. I still think that's a little bit too much. So that means you need a harder strength alloy. But remember, it's not so easy because then you need to find the proper machine to mill the shape and then smooth it out, okay? And you also I can also use the method to calculate the eigenfrequencies. So the reason why you need to know that is because the natural frequencies are significantly reduced in water compared to air. For example, 1.7 hertz compared to 2.9 hertz. And that's due to added mass effect. The reason you have to is because you basically have to move the water in addition to moving air with it. If you swim, you can see that there's a much more resistance, and it's due to added mass effect. So then the reason why you need to worry about it is because if your excitation frequency matches the natural frequency of the structure, you end up with resonance. So you really don't want that. So you need to know what kind of frequency you got. So now if I analyze this structure under tidal boundary layer flow, where the velocity varies with depth, for example, and let's say I do a realistic situation, 20-meter diameter, and then let's say the seabed is 5 meters from the tip of the blade at the bottom, and then the surface is 5 meters from the tip of the blade. If I actually analyze this, I can use the method to see how does the pressure varies as it rotates, and I can also see how I can integrate it, then I can calculate the force. You can see that even though the flow, what happened is this would be, for example, the loading on the first blade would be here, and the loading on each of the blades is sort of like sinusoidal because it's periodic, right? It goes around. So this is the first blade. The red is the first blade. This is the second blade. It lagged by 120 degrees since this is a 3-blade, and that's the third blade. So that's why you want a 3-bladed design, so that the loading cancels, sort of like well balanced. It balances out. So you see that the resulting thrust and power is pretty smooth. And you can compare that against the steady design. And so we can actually calculate, we know how much bending moment that will cause, not just the turning moment, but also the bending moment, so that we can design it carefully, okay? And we can calculate the resulting power for this, which is 1.1 megawatts. So, and I can calculate the stresses, how it varies with angle and displacements. And now the final thing is, what if I need to, so how does this translate if we actually use it? So let's say we put in a variable speed engine design so that it starts to rotate at 0.5 meter per second, and the rated speed is 2.5 meter per second, assuming the velocity, the rotor speed can vary with the flow velocity linearly up until your 2.5 meter per second. This is by controlling the pitch and the yaw. And the reason why you want to do that is because you don't want to, when the flow goes really fast, you don't want to keep spinning because you end up with overload. You'll tear up your drive chain, you'll tear up your blades, and et cetera. So if you do that, you end up with this power curve. So you can generate about 1,000 kilowatts, okay, or 1 megawatts. Now, if we actually put this one in San Francisco, let's say this is the tidal velocity data for the San Francisco Golden Gate Bridge site. So we can, like, there's data on how does the velocity vary throughout the year. You can change that into a frequency plot. And so if I actually put this propeller, this turbine into the water and see how it performs, I will know that I can get a total of 2,752 megawatt per each 20-meter turbine. So that's pretty good. So what are some design challenges that we have to worry about? And this actually applies to both wind and tidal turbine because a lot of these issues also have to deal with large-scale, particularly offshore wind turbines. So on the hydroelastic side, which means the combination of hydrodynamic and structural dynamics, you have to worry about the blade design. You also have to worry about site selection. You have to, and some kind of passive control technology. I'll mention that in a little bit. And then how do you support the structure, particularly if it's in water? And about extreme loads, for example, if you have impact, and the durability in a harsh sea environment. Preferably, you don't want to, if it's for tidal turbine, you don't want to maintain it constantly. Just sending something is expensive, and taking it out is expensive, right? So you want some kind of sensor. You need some kind of sensor to detect the structural integrity, how good it's performing, and then so that you don't have to constantly go down and check it and maintain it. That's really expensive. So you need, and you also want some kind of control technology so that it can change in direction. So to go along with the flow. And that has some complicated issues about how do you balance the power, the design, et cetera. And then you also have to have actuators that will not fatigue and can deliver enough power. In water, that's a much more significant issue. So where we want is the integration of these three different fields. So there's a lot of work to be done. And the outcome is you want a system that is reliable, robust, and cost-effective. And you want to also reduce the impact to the local marine life, and then also to the environment, and then reduce the noise. So all of this. So what are some, I want to end this talk, I think that's good timing, with some of the ideas that are being toyed with the wind industry side. So they have talked about using composites. So this is the new STAR turbine. It's called STAR for Sweep Twisted Adaptive Rotor. And basically it's composite, it's hollow architecture, and it's designed such that when it bends, it twists so that it changes the angle of attack, make it more efficient. I have designed similar systems for marine propellers. But when you put it in water, you cannot use hollow architecture simply because the load is so high. So we use different kind of laminates and we stack it so that we take advantage of the material-induced bending, twisting, coupling. So you can see an example of manufacturing of this. There are some other technology that's being toyed with at Sandia National Laboratory. For example, trailing edge flapping mechanisms, micro taps. So you see the trailing edge. Basically, you want to be able to flip. If you look at airplane wing, when you land, you see this flap coming out. So the same idea so that you can brake when it's at very high wind. Now, in water, you have to be careful because the loading is much higher. It can easily tear off that little flap. And you can also, if you have any kind of gaps, like for example, this one have little flaps. If you have gaps around here, you can form cavitation in there because the velocity can be high. You can have growth, or you can have corrosion in those areas. So it's much more complicated in water. So some of these, and also your actuator unit to power them, it has to be much higher power because of the water that you're pushing against fluid than in air. And it gotta be durable. So these are a lot of these technical challenging issues that we gotta deal with, but we also have a lot of ideas, right? So that's the end of the talk. Thank you for your attention.
Hey, questions for Julie?
Yes, there's definitely opportunities for active and passive control to reduce cavitation. And the main thing is really how can you control the angle of attack? If I can, for example, if I can reduce the angle of attack, if I can reduce the local velocity, then the pressure will not drop, will not be lower to such a degree that cavitation will happen. So there's definitely, and particularly near the tip. So if you have some ideas, let's talk. Yes.
Can you talk a little bit about the impact on the environment and marine life? I know you said that it's an unknown, but there must be some information on that.
Yes, so like you can, for example, remember one of the earlier photographs, you have a duck around it. So like one area is you can actually put a shroud, what we call shroud or duck around it. And there's one advantage of that, obviously, you can put a screen in front so that the fishes wouldn't be going through this. And another advantage with that is that you can, if your area in front is bigger than your turbine area, then it takes a much greater flow area drawing into, so you can actually increase the efficiency of your structure. Now, but that results in increased costs. Right? So it's a balance. And so you have to work, and then also you have to think about, it depends on what kind of application. You know, personally, if you were to, for example, take advantage of ocean current energy where you put these turbines in the conveyor belt, now that's also the area where you have a lot of marine life that actually go through. So that may not exactly be a good idea because that will change the life cycle of these animals that we want to preserve. And then you also have to worry about how would that, if you take a tremendous amount of energy from the flow, let's say you use tidal turbines, and you take a tremendous energy from the flow, how would that affect the local ecology? So you have to do some estimates in terms of how much energy you're putting, and how would that change, for example, the sediment transport characteristics? How would that change the flow pattern? And especially, you know, like, for tides, it's not so affected by global warming, but for some other like ocean wave or ocean current, it may be more affected by global warming, rise in seawater level, for example. So I think that's a great area that you need to do research, and you want to make sure that, for example, you don't want too much noise underwater because that may affect some animals that are sensitive to them, or you don't want if you have electromagnetic device, again, that may be sensitive to some animals. So I think in the design, that's why you need different groups. You need biologists, you need policy makers, and you also need engineers so that you can discuss together to understand what are the important issues and how do you design for it. Yes.
Yeah, I'm just sort of curious about the degrees of freedom in the design. I mean, there's sort of an aspect ratio for the blade. There's a question of the number of blades on the hub. I mean, and so you could have 3, 6, 12, and you know the natural frequencies would be very different for different aspect ratios. So I'm just sort of curious why it would come out with 3 blades with a long aspect ratio, given that that's what people have optimized for a very different viscosity and very different flow regime. Where do you think the sweet spot for the design is for the, for the water environment?
Well, 1 blade, you have unbalanced loads, and it's not very, 3 blade is a good balance. In terms of number of blades, a good balance between efficiency and the load balancings, because you don't want really unbalanced load transfer to your control structure, your drivetrain, et cetera, and the rest of the load that the support pile got to take. But in addition to that, it's not just the number of blades. If you look at the wind evolution design, the beginning one just look like things that are toy, and the new one is like they have sweep. So like in marine industry we call that skew. So it's like this. So if you look at a lot of marine propeller, it actually is skew, and the reason is because when it rotates, so you have the leading edge coming in, and then this slowly coming in. So it doesn't just boom, impacts the water, right? You don't want to crash a Coke can in water because that can cause it can cause more damage, and then it can cause tip vortex cavitation and vibration near the tip. So we don't want that. So you want a more generally curved design so that it enters the water, cuts the water more gradually and more smoothly, so you don't run into these tip vortex cavitation, tip vortex vibration issues, and the associated vortex blade interaction that associated with it. So, and you want to change the pitch the pitch is whether you want to do this, because the pitch changes the angle of attack. You think about airfoil. You streamline it versus if you do this, then you have a lot of stall. But you may want to use stall to purposely stop it at very high winds. And you also have rate, so it's rather skew rate forward or backwards. So there's a lot of freedom. And what I did was I have developed a generic algorithm where you can, for example, we can define all those as a sectional characteristic and then optimize them so that we can come up with the optimized blade geometry. And we have done that a lot in the marine industry side. I mean, obviously, you see the marine propellers, especially some of them for naval applications, they're really highly advanced so that you really don't get cavitation.
You showed a chart about wind and how long it took wind to get to a place where it was,
Yes.
seemed viable and practical. Where are we along the line on this?
We just started.
Okay, so 20, 30 years.
I think it will take less than 20 years, maybe about 5, 10 years, because we're not starting from, there's like we can borrow some of the technology from the wind energy side as well as from the marine propeller side. So we're starting at a higher block than just the first one. So that's why I think it will be faster. Yes.
I'm curious what kind of software you use to do the stress strain analysis and bending analysis.
I actually use Abacus over there, and then I couple it with the fluid solver that I developed. So so I write that routine into there, and then to do the coupling. So it's a finite element analysis software. Is 3-dimensional, and then the nice thing about it is I can also use. I would like to apply some of the techniques that I use for propellers, so composite, so that it can automatically change angle, so the shape changes with the flow. So that's what I use. Yeah. Yes.
I just have a question. Are there any advantages to having like, smaller blades and just a larger array of threads? Would
Yes.
that
Definitely. Well, you know, if you reduce the length of the blade, your moment arm is smaller, so your load is much lower. So you don't need all these high corrosion resistant, high strength material. You can use a lower, so it's easier to machine. So as a result, the cost may be lower. But now you have to remember the power. You also get less power. So then you need more of them, right? Then you have to worry about spacing. Like in the ocean, you don't want the weight of one to interact with another. So like the power is proportional to the area, the sweep area, as well as with the flow velocity. So if you want to use something smaller, then you also need more if you want the same amount of power. Yeah. Yes.
For more of a civil application, if you had, say, a river where you didn't really want to build a dam, but you did want some method of flood control, could you put like oversized turbines in the river and have that at all contribute to flood control issues, or does it not really work very well?
You need a lot of them. So, yes.
You may have talked about this earlier, but I came late, but excuse me if I'm repeating something. But there's been some work going on in Michigan on a different kind of structure, which is a more horizontal structure, which oscillates up and down.
Yes.
Which claims to work better in low velocities. Are you familiar with that?
Yes, I actually showed a picture earlier. Yeah, I have projects together with the University of Michigan group. Actually, I can meet them in Florida next week. So what that does is take advantage of vortex-induced vibration. The flow goes to, and then it takes account of the frequency, and then you run into resonance, and then it just fluctuates like this. Now, they have tested successfully at the lab, and I think it's a very, very beautiful device. But you have to think about, you know, when you put it out in the ocean, now you have to think about how to secure it, right? So one example why that becomes a problem, for example, there's some of you may have seen it on the news about a point absorber device designed by Oregon State University, and that basically, again, move up and down. And so, how it converts to energies, I don't know if some of you have used those flashlights that you shake it, you don't need battery, and you shake it, and then it can turn on. It's the same mechanism. But now the problem is it worked beautifully in the lab. Once out in the ocean, it broke down. Why? Because you have varying sea state, okay? So the wave can be the significant wave can be higher. And what happens because these move up and down, the wave was so high, it clocked up and it never came back down. So you have to, some of these, that's why that's why field testing is so important. I mean, in the lab, everything is controlled. Out in the ocean, you have a different story.
That's just an engineering problem. That's not a theory problem, though.
Yes, I mean, the theory, but your theory, you have to, for example, a lot of the design on wind turbines assume uniform flow. So you design for the average performance. They don't account for this. So this is the first one. If you look in the literature, you don't see other methods that account for the structural part as well as for how it varies with flow. Now, why that is important? Because now you have a certain frequency, the sampling frequency of each blade becomes higher, and if that matches, you can get resonance and it can break. So yes, it's an engineering problem, but it's an engineering problem that you have to consider. You cannot say, okay, I cross my finger, hope that it works.
One last question.
I've seen some information on chemical turbines, that they're vertical axis, but they have a varying angle of attack over the length of the blades.
Yeah,
So if you might comment on this.
I don't have, I mean, it's not that easy to design, especially if you want the flow to come in from this angle and for this angle, because it's bound to be not optimal at one of the angles. That's my opinion. So I would prefer to use turbines rather than the 8-beater. And the drag device there are just really inefficient, so I don't recommend them.
Well, thanks very much, Julie.
Thank you.